So in part 2 of the continuity at a point video, we're going to begin with discontinuities. So we have 3 images of what looks to be a very similar graph on the page now. In example A, we have a point at 0, 1, and the line continues on forever. And we would say that this is an example of a continuous. Let's try that again. A continuous at x equals 0. But in part B and C, we see discontinuities. In part B, there exists a hole at x equals 0. And the function continues on in the other direction. So what we see then is the two-sided limit exists because as the limit approaches x equals 0 from the left and x equals 0 from the right, they both approach the same number, 1. However, the function doesn't exist there. So the two-sided limit cannot be equal to f of 0 because f of 0 doesn't exist. Over on part C, this is also a discontinuity. Again, we have a hole at x equals 0, and the hole has actually been filled. It's just been filled in the wrong spot. So there's a point there at 0, 2 that is just not in the right place. Both of these types of discontinuities are called removable. They're called removable because discontinuity can be removed by setting f of 0 equal to the limit as x approaches 0. In other words, you can remove discontinuity by changing just one point. We would add a point to part B, and we would move a point in example C. So these are called removable. Here we have 3 other types of discontinuities, and all 3 of these are non-removable. They're non-removable because discontinuity cannot be removed. Discontinuity cannot be removed. So what are these 3 types? First up, there is the jump discontinuity, and we might call that the jump discontinuity because obviously if there was a little person standing on this part of the function, he would have to make a leap and jump to be in the next part of the function. Part E, we have what's called an infinite discontinuity. And in an infinite discontinuity, I think it's pretty self-descriptive. The function undergoes a vertical asymptote, and the function either goes up towards positive infinity or it may go down towards negative infinity on the y-axis. I think this is a good chance for me to draw a little skateboarder here. Traveling down. There he is. Woohoo. And then finally on part F, we have an oscillating discontinuity. And so what happens on F is as we get closer and closer to 0 on the x-axis, this function jumps up, down, up, down, up, down, up, down, up, down, and isolates between 1 and -1. And so this function never kind of levels off and behaves well towards the x value of 0. So those are the types of discontinuities. In the next slide, we have an exploration. And what we're going to try to do is look at a function and remove a discontinuity. So here's the function. F of x is equal to x cubed minus 7x minus 6 over x squared minus 9. Step 1 in our explanation, we're going to factor the denominator and then give the domain. So this denominator, I believe, factors into x minus 3 times x plus 3. So that means the denominator of this rational function is 0 at both x equals 3 and x equals -3. Therefore, the domain of this function must be negative infinity to -3, non-inclusive, union with -3 to +3, non-inclusive, union with 3 to positive infinity. Because a rational function is the quotient of 2 polynomials, we should have continuity everywhere that the denominator is not 0, and it just so turns out that at 3 and -3, the denominator is 0. Next up, we want to investigate the graph of f around x equals 3 to see for sure that f does have a discontinuity at x equals 3. So let's take a look at the graphs. We're going to pull up our graphing calculator and hit the y equals screen. And let's start typing in this function's rule. So we have x to the third minus 7x minus 6, and that's on top of x squared minus 9. And let's go zoom. I like zoom decimal. Let's try this. And we should start to see a graph of the function. And yeah, it looks like where x is equal to 3, we have a hole in the graph. And I think I can even make that a little bit bigger. Yeah, it's easy to see here where x is 3, there is a discontinuity in this graph. So let's keep that in mind, and let's go to the next step where we have how should f be defined at x equals 3 to remove the discontinuity. So back to the graph, we can move the detached LCD again. Let's hit the trace button, and let's take a look at, as we move the x value closer and closer to 3, what the y value does. So let's get over here. So we're at 2.5 now. So y value is 2.86, 2.95, 3.05, 3.14. At 2.9, we are at 3.238. At 3, there the function's undefined, and on the other side, 3.427. So on one side, 3.427, on the left side, 3.23. So it seems to me like somewhere around 3.3 would be a pretty good guess. So let's say that for right now, 3.3. Then number 4, we want to show that x minus 3 is a factor of the numerator of f and remove all common factors. Then compute the limit as x goes to 3 of the reduced form of f. So we need to show that x minus 3 is a factor of the numerator. This isn't a quadratic polynomial that's pretty easy to factor, but I think by synthetic division, we can come out with the quotient. So we're going to stick a 3 here. That's the opposite of negative 3. Then the coefficients 1, 0, negative 7, and negative 6. Put that 0 in for the x squared term. So by synthetic division, we drop the 1. 3 times 1 is 3. 0 and 3 make 3. 3 times 3 is 9. Negative 7 and 9 make 2. 3 times 2 is 6. And we have a remainder 0. So that means this is 1x squared plus 3x plus 2. So this function is equal to the factor x minus 3 times the factor x squared plus 3x plus 2. And this is all over x minus 3 times x plus 3. So that common factor of x minus 3 can be canceled out or removed from the original function to create a new function, x squared plus 3x plus 2 over x plus 3. Number 4 says take the limit of that reduced form for f as x approaches 3. So what is the limit as x goes to 3 of x squared plus 3x plus 2 over x plus 3? So this can be done by direct substitution. We'd have 3 squared is 9, plus 3 times 3 is another 9, plus 2, over 3 plus 3. So that comes out to be 26ths, which is 10 thirds, which is approximately 10.333. So, or sorry, 3.333. Let's try that again. 3.333. Or 3.3 repeating. So our guess of 3.3 by the graph was a pretty good guess. Finally, we want to show that the extended function g below is continuous at x equals 3. The function g is the continuous extension of the original function of f. So what we've got here in g is a piecewise function that has been defined as our original function f everywhere except where that hole in the graph was. And then at x equals 3, where the hole existed, we have inserted the point 10 thirds. So there's a point on this graph, 3, 10 thirds, essentially there to plug the hole that existed in the original function. How would we show that this function is continuous at x equals 3? Well, by its definition. We would want to take a look at the limit as x goes to 3, two-sided, of the original function here, which is f of x. And we want to make sure that was equal to g of 3. And what may make more sense here is replacing this f with the g, since the g function is the f function everywhere except for 3. And we just found that limit. It's 10/3. And g of 3, by definition, is 10/3. And since those two are equal, then our function is continuous at x equals 3. So that's the process of removing a discontinuity.